By the way, some of you may notice that my face looks a little weird. So I actually just got in an argument with a string theorist a couple of days ago, and things got ugly. So yeah, this physics is not for the faint of heart. Anyway, thanks for showing up, everybody. I'm John Horgan. I'm director of the Center for Science Writings at Stevens University, Stevens University of Stevens Technology Institute. And I've been running this lecture series for a really long time. I want to tell you quickly about an event we have coming up on November 2nd. We have a talk by a political scientist at Harvard named Erico Chenoweth, who is an authority on nonviolence. And she's going to talk about how and whether nonviolent activism can work in our obviously very violent world. But today, we have a talk by one of my favorite scientists and one of my favorite people, Sabine Hossenfelder. She is a very blunt, courageous, clear-thinking physicist who is renowned for her blogging and for posting videos online. She's got a huge YouTube following now. These videos tend to be 10 to 15 minutes long on, I was just looking up some recent topics. Does the past still exist? Did the Big Bang happen? The multiverse, science, religion, or pseudoscience? Is nuclear power green? So not only theoretical physics, but she also gets into practical questions related to physics. I had Sabine come to the campus 4 years ago to talk about her first book called Lost in Math, which is really a fantastic book, a blistering critique of modern theoretical physics. She's got a fantastic new book out that's already a New York Times bestseller called Existential Physics. I highly recommend it for everybody out there. It's really informative and entertaining and profound. So I am thrilled that Sabine can be here to talk about some of the things in her book today. If you have questions you want to submit to her at the end of her talk, please submit those by chat. And so now we're all giving you a virtual big round of applause, and please make sure you're all muted if you're not already out there. So great to have you here, Sabine. Sorry about the technical snafu.
No, it's fine. My talk is a little bit on the short side anyway, so I was almost feeling bad because the last time I gave it, it was too short. Yeah, thank you so much for the introduction. Actually, like half of the topics you just named will actually be in the talk, and yeah, I do talk about a lot of different topics on my video channel. Excuse me. I actually recorded a new one today, and guess what it is about? It's about long-termism. And then I open my computer and I look at it and I see that John just wrote an article about long-termism. Okay, so I'm going to try to show you my slides. Does this work so far? Do you still see the slide full screen?
I see it full screen, yes, with a little box of you in the corner. So that looks good.
Okay, wonderful. Okay, hang on, I just have to move you away so you're not in front of anything that matters. Okay, yeah, so I saw that I was announced with talking about the meaning of life. So I'm afraid I don't know the meaning of life, and I'm not going to talk about it. But I'll talk about the next best thing, which I called existential physics. Or actually, it wasn't my terminology. My editor came up with this as a title for the book. The original title of the book was More Than This, which is also why the book ends on those 3 words, which I struggled very hard to make work. And then, of course, in the end, it was all for nothing. But when he came up with it, I was like, this sounds really good. Sure, let's take it as title. He wanted to get the word physics in there, and I thought it made sense. But of course, it brought up the question, like, what the heck is existential physics? So I made up some definition, and I thought what makes sense if you read the book is that it's about those aspects of physics that concern human existence. For example, the nature of time, what changes, the beginning of the universe, where do we come from, the structure of matter, what are we made of, and limits and constraints, what can we do, what can we know. And so broadly speaking, it's a summary of everything that I find the most interesting in the foundations of physics. Now, those of you who've known me for some time might think, well, this is quite a change of direction. I guess I'm somewhat better known for, as John already said, being very outspoken if something doesn't quite sound right. So I'm typically the person to criticize headlines, if there's some nonsense making rounds being shared widely on social media, like physicists create negative mass, then I'm the person who goes and says, no, they didn't. Or they detected evidence of parallel universes. No, they haven't. Faster than light travel could work. Well, no, it can't. So I guess that's what I normally do. And I have to, so I think this is really important. And of course, I'll continue to do it. But I also think that it paints a very one-sided picture of physics. It gives you this idea that physics only tells you what can't be done. But I think that physics has another side that I wanted to talk about in my book. It tells you what is possible. And so the way that I think about the topics in my book, excuse me, is that they lie in this blurry overlap between science, philosophy, and religion. And well, they do have their mean values, so to speak, in science, but I'm trying to figure out exactly where does it blend over into philosophy and in religion, and not always have the physicists remained on the side of science. And so I'll give you some examples for this in the following. So when I wrote the book, I constantly said, well, this is for all we currently know. So what I'm going to talk about is for all we currently know, and this is blah, 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 for all we currently know, it's so and so and so on. And in the end, I just put it in the preface and then wrote, everything I'm going to say is for all we currently know, unless otherwise stated. And I'm going to do the same in this talk. So everything could be revised if we collect new evidence, if there's better data, if we learn something new, and so on and so forth. And I'm going to start with indeed the first topic that John mentioned: does the past still exist? So it's actually a standard textbook argument that students in physics are all exposed to in the second year or something. Depends on exactly where you study. But it's something that I think most people are not exposed to, and they tend to find it surprising. When I learned of this the first time, and I think everyone has this reaction, I found it hard to believe. And for some days you walk around like feeling a little bit weird because your whole understanding of reality just made a noticeable shift. But then at some point you become used to it, just because you have to move on with your life. And so partly the reason I wrote the book was that I wanted to remind myself of those things that I once found so very surprising, and that the question whether the past still exists is one of them. So this whole argument is based on Einstein's theories of relativity, special and general relativity, but for this is actually sufficient to talk about special relativity. And it's, loosely speaking, it's based on three axioms, you could say. One is that the speed of light is finite. It's the same for all observers, and nothing goes faster than light. Strictly speaking, this is just true for the speed of light in vacuum, but this is theoretical physics, so everything takes place in vacuum anyway. And this sounds really, really innocent. And of course, to be honest, it's a little bit more complicated than this, but this is like the briefest of all brief introductions to Einstein's special relativity. It has some funny consequences. So take, for example, the assumption that the speed of light is finite. Well, you could ask yourself, so am I here now? Well, of course, in this scenario, the example doesn't really work because for all this could have been pre-recorded and you're just watching it. So maybe you should better ask, is the screen that you're looking at there now? Well, the speed of light is finite, and the speed of light is also the fastest that anything can go. So strictly speaking, you can't see the screen or me the way that it is right now, because it takes a certain amount of time for the light to travel from the screen to you, and everything else is just slower than that. And this brings up the question, like, if I can't actually see what's going on now, then what do we mean by now to begin with? And well, I guess most people have the reaction, well, this is just insane. Why are we having this conversation? But I guess you're not most people, because otherwise you wouldn't listen to a talk about existential physics. So it's worth investigating this question a little bit more. What do we mean by now, and what does Einstein's theory say about it? So here's a simple thought experiment. As you certainly know, Einstein was a big fan of thought experiments, and this is one that he liked to talk about, which illustrates this problem with the notion of now. So suppose you're standing on a mountain or something, and you're watching some kind of train or I don't know, a tram or something going by from the left to the right in this picture, and you have a friend who's exactly in the middle of the train, and you're looking straight at her. And if this little train or wagon or coach or whatever you want to call it is directly in front of you, so that you're looking directly at her, then there's a mechanism that will ignite flashes on both ends of the train. And the question is, do those flashes, do you see them at the same time, yes or no? So if you were trying to reconstruct when they happened, would you say they were simultaneous, yes or no? Now, from your perspective, the answer is pretty obvious, because this entire train or wagon doesn't really matter at all. You can just take it away. And by construction, those two flashes came from two places that are exactly the same distance from you, and the speed of light is always the same. So of course they arrive at the same time at your location, and you would say, yes, they are simultaneous. They were emitted at the same time. Okay, but now how does it look like from your friend's perspective? Well, in the time that the light from the flashes travels towards her, she moves a little bit to the right. So from her perspective, the flash from the right arrives earlier than the one from the left. And she would say, no, they're not simultaneous. So in your attempt to reconstruct what happened at the same moment, you and her, you disagree. And this may seem like this is just, some weird setup, some weird construction, and what's all this stuff with the train and the flashes and this weird mechanism and so on. But it's just one example of what's generally the case in special relativity. There is no way to construct a notion of simultaneity in any way that does not depend on the observer. And for this reason, this idea that something happens now elsewhere, which relies on this reconstruction of what happens at the same time, depends on the observer, which has the weird consequence that your past is somebody else's present, or the other way around. You know, your present is somebody else's past, or somebody else's future. So there are only two logical conclusions you can draw from this in Einstein's theory of relativity. It's either that nothing exists now, so this is logically possible. You could just say the only thing that exists is what goes on in my brain. And this raises some further questions like exactly how far can it go? Why is it only your brain? Why not one particular synapse or whatever? Or the other logical possibility is that all moments exist the same way, and this is, I would say, the more generally accepted one. It has a name. It's called the block universe because it just sits there. It doesn't come into being. There's no special moment that you could call a now. All those moments in this block universe exist in the same way. They're just there. And that's a consequence of Einstein's theories. And now it's certainly the case that we perceive one moment as now, but this is just an artifact of us being inside the block universe. So we sit in it and we can't have this outside view. Now, this is a consequence of Einstein's theory of special relativity, and when he came up with it, he didn't know of quantum mechanics, or rather, quantum mechanics was not well established at the time. So when we look at it today, it's a little bit more complicated for what the future is concerned. So this argument still goes through for the past, but in quantum mechanics, you have an indeterministic element in the measurement process. So each time you make a measurement, then the time evolution of the entire state, which is described by a wave function, makes an indeterministic random jump. And it's not random because you don't know exactly what it depends on. In quantum mechanics, if that's the correct theory, it actually can't be predicted. So it's fundamentally random. So this leaves the possibility open that the future is not yet fixed, but it's kind of controversial. This story about the block universe and that the past still exists, I would say, is actually quite uncontroversial, at least among physicists. There are certainly some who disagree with it, and papers have been written about it, but I would guess that most physicists would kind of agree with this. So does the past still exist? For all we currently know, yes, it does. So then let's move on to the second question: can information be destroyed? It's actually very closely related to the first question, because it touches on this question of can things cease to exist, or do they just continue to exist? So to understand this point, you have to know a little bit more about how the fundamental laws work that we use in the foundations of physics. They all work the same. So we have something that's called an initial state. That's a full description of whatever it is that we want to describe, which we generally call a system. So the system is just a weird word for the thing that we want to describe. But in the simplest case, you probably remember this from school. It could be something like the initial position and velocity of an arrow or something like this. So this would be the initial state. In quantum mechanics, it's all a little bit more complicated. I'll talk about this in a second. And then we have an evolution law that allows us to calculate what happens later. And actually, this also works the other way around. You can also use the evolution law to calculate what happened earlier. We do this, for example, in cosmology. So in cosmology, we take the state of the universe at the present time, and then we use the evolution law, which comes from Einstein's theory of general relativity, to figure out what happened earlier, and with the aim to try to understand how the universe began. So this is how it works. So we have those one-on-one maps that we call the evolution law, and they are all in principle time reversible. So in practice, of course, they often aren't, because we're missing information. So this is why in thermodynamics we talk about irreversible processes. But in principle, fundamentally, if you knew all the details of the particles and so on, you could turn it back in time. And so what we often talk about when we have this kind of scenario in mind, when we say information, we're really talking about just the data that you need for the initial state. So in this sense, the information that is contained in the initial state can't be destroyed. It's just reconfigured. So the particular arrangement of the elementary particles changes. But if you knew exactly what it is, if you could just measure it, you could always calculate back what the earlier state was. So I'm formulating this so carefully when I talk about information, because there are other areas in physics where the word information means a little bit more, but at least in this context, it just means all the details that you need to describe whatever it is that you want to describe. And so this pretty much looks like, okay, case settled, information can't be destroyed, evolution law goes forward and backward. But so there are two exceptions to this. The one is the measurement in quantum mechanics that I just already briefly talked about, and I'll now tell you a little bit more about it. And the second one is black hole evaporation. So what happens during measurements in quantum mechanics? So in quantum mechanics, everything is described by a wave function. The wave function, there are wave functions for everything. I mean, at least theoretically, it's not just for electrons or elementary particles in general, but also for atoms and molecules and you and I and the entire universe. For everything, there's a wave function. And this wave function in standard quantum mechanics is just a device to calculate probabilities. The wave function itself cannot be observed. This is why people say quantum mechanics is weird, but that's how it is. And now the thing is, suppose you have a wave function that tells you the probability of a single particle being in a particular place, which is what this sketch on the left is supposed to show. So, and it's 60%, it's in this one in this one spot, 40% on the other spot, roughly something like this. And now you go and measure the particle. Well, after you've measured it, you know with 100% probability where it is. It's where you've measured it. So what this means is that in this process of measurement, you have to update the wave function. It's sometimes called the collapse of the wave function or the reduction of the wave function. It's all the same thing. It means that after you've made the measurement, you know where it is. So you have to change it. And this update of the wave function is not reversible, because if the only thing you know is that you've measured the particle in one particular place with 100% probability after you've done it, you can't infer what the earlier state of the wave function was. Might have been, it was just exactly the same. It was 100% in this place all along, or it was 60% probability that you'd find it in this place, or maybe it was just 5% probability and you got really lucky. So the measurement process in quantum mechanics is not reversible. You cannot from the final state infer what the initial state was. So measurements in quantum mechanics seem to destroy information, the information about what exactly the wave function was. But do they really describe what actually happens? So Einstein's big misgiving about quantum mechanics was that this update of the wave function is actually non-local. It happens instantaneously, everywhere in space. In principle, mathematically, that's what happened. And we already saw earlier, like the special relativity, Einstein's theory, has a problem with simultaneity. It depends on the observer, so it's not even clear what this actually means, that you instantaneously update it everywhere. And Einstein didn't like it at all. This is what he called spooky action at a distance, like this instantaneous update of the wave function. And quite some physicists, I don't want to say most of them, but there is a certain fraction, think that the measurement update isn't fundamentally what happens. And I'll admit that I'm one of the people who think that this is probably just some description of an underlying process that we haven't yet fully understood. It's probably just an approximation, which opens the possibility that this underlying law might actually be deterministic and time reversible again. Also, this entire measurement story in quantum mechanics brings up the question, like, what's with the entire universe? Who measures the universe? What sense does this make? So yeah, but I guess the answer is we don't really know what's going on. And then the other thing is black hole evaporation. If you throw something into a black hole, then it vanishes behind the horizon, and you have no way to figure out what happened with it. So if you throw something in that carries information, like, for example, a book or your phone or what have you, then it seems to be lost. Now, a priori, this isn't a big problem. It doesn't seem to have any fundamental significance because, I mean, you could also put your book into I don't know, a chest or something, and you lock it, and then it's gone. For practical purposes, you can't retrieve the information that's inside of it, but it doesn't mean that the information was lost. It wasn't destroyed or something. And in principle, it could be the same with black holes. And indeed, that's what people thought until the 1970s or something. And along came Stephen Hawking. And Stephen Hawking said, well, those black holes, they don't sit there eternally, but they emit radiation, which is now called Hawking radiation. And this radiation is entirely random. So it doesn't contain any information except for the mass of the black hole and the angular momentum and the electric charge. So it does have like 3 bits of information. But almost the entire information of everything that fell into the black hole and what formed the black hole in the first place can't be in this radiation. And so this radiation carries away energy from the black hole, which means that the mass of the black hole has to shrink, and it shrinks until eventually it's entirely gone. And the only thing you have left is this entirely random Hawking radiation, which doesn't contain any information about the initial state of the black hole. And so this too is an irreversible process, because if you have this final state of the Hawking radiation, you can't tell what formed the black hole initially. So this too seems irreversible. And I guess, as you probably know, there's a big controversy around whether this is actually true. This is called the black hole information loss paradox. The problem is that this process of evaporation, if it's indeed not reversible, then it's inconsistent with quantum mechanics. And this is because this irreversibility happens in the mathematics already before you make a measurement. But without the measurement, quantum mechanics should be reversible. So it's a mathematical conundrum. We don't know how those two things could possibly fit together. And Hawking originally thought that black hole evaporation is actually irreversible, and it's inconsistent with quantum mechanics, and something has to be fixed about the processes in quantum mechanics. But later in his life, he came to change his mind and thought that actually it's reversible. I think most physicists now believe that something is missing in Hawking's calculation and that this process is actually reversible. I think so too. But we can't experimentally test it. The reason is that the black holes that we can observe, so the astrophysical black holes out there in the centers of galaxies or stellar mass black holes and so on, they just take way too long to evaporate. So actually at the moment they don't evaporate at all, because the Hawking temperature is so low that even the temperature of the cosmic microwave background is higher. So they actually gain energy from the cosmic microwave background. But this will cool if the universe continues to expand, then the temperature of the cosmic microwave background will drop and eventually they will start to evaporate. But until supermassive black hole evaporates, it takes something like 10 to the 99 years or something ridiculous. So that we can't experimentally test it. So really the answer is we don't know what's going on. So can information get destroyed? Depends on what you believe happens in the measurement, in quantum mechanics, and in black hole evaporation, though I think the answer is no. Then let's move on to, again, this is related to the previous question. Of course, that they're all kind of related, but I'm going to talk about the question, how did the universe begin? And before we can talk about this, I have to tell you a little bit about how modern cosmology works. Modern cosmology is based on Einstein's general relativity. So this is the theory which says that gravity is not a force, it's actually caused by the curvature of space and time itself. According to Einstein's theory of general relativity, the universe expands, and we can tell from our observation that not only does it expand, but that the expansion actually speeds up. And just from observing exactly how it expands, we can calculate back, we can determine the amount of matter and energy in the universe. This is how we get numbers for the fraction of dark matter and dark energy and normal matter. And this is a pretty good model for the universe as a whole. It's made a lot of predictions, the formation of structures, how fast they form and how they're distributed, the cosmic microwave background and its properties, the abundances of light atoms, redshift of distant galaxies, and so on and so forth. So it's a pretty good theory. Now, what we can do, as I said earlier, we can extrapolate the present state back in time. And what happens if we just extrapolate the equations of Einstein's theory back in time, then the energy density of the matter, and also this of dark matter, by the way, and the curvature density of space, they become infinite. And this happens at a finite time, at about 13.7 billion years before now. All those quantities just go to infinity, at least in the mathematics. And this is what we call the Big Bang, or at least this is what was originally called the Big Bang. And so this is what the math says, but no one thinks that this is actually what happened, because this singularity in our mathematics almost certainly just means that the equations break down and they would have to be replaced with better equations, some that are able to also describe the quantum behavior of space and time itself. So for this, we would need a theory of quantum gravity, but we don't have one. And so I think the answer to how did the universe begin is just, we don't know, because we can extrapolate those equations back and then we get the singularity, and that's probably not what happened, and that's the end of the story. But for a lot of physicists, it isn't the end of the story. And for this, we have to talk about the way that those laws work again. So remember, as I said earlier, we have an initial state and a final state, and then we have this evolution law that can identify one with the other. And we can do this forward and backward. And when we're talking about cosmology, we're talking about using the evolution law back in time. But now the issue is, if you have an evolution law and you have an initial state and you apply the evolution law to it, there will always be a state on the other side that will fit to the evolution law. So you can just take whatever evolution law you want, and then you take the initial state for the entire universe that you get out of this particular evolution law, and then you have the right initial state and the evolution law. They will always fit together. So it seems that we can't ever find out what the right law is. And the situation isn't quite as bad, because we have another requirement for how theories work, is that they should be simple. And so this is basically why we pick out a particular model for the cosmology of the universe. It's because this is the simplest way to do it. You could always, in principle, you could take another evolution law, and this would give you some initial state, but in general, this initial state will be hideously complicated, because the different parts won't fit together. For example, the cosmic microwave background won't fit together with the formation of structures. You would have to have a really complicated initial state for either of them. But in the theory that we currently use, they both come out of the same initial state, basically. Okay, but in principle, what you can do is you can go back in time to a time that's so early that we don't have any observations that could allow us to constrain the equations or their initial state. And since we don't have any evidence for what happens at really high energy densities in the early universe, we just can't look back in time that far. We can change the equations, we can change the dynamical law, and then you get different initial states if you roll back those equations further and further. And this is why there are so many theories for the beginning of the universe. If you change those equations back in time, you don't get the Big Bang. Maybe you get a bounce. So so the energy density doesn't actually go to infinity, it goes to some finite value. And if you trace it back further in time, you find that there must have been an earlier universe, which was kind of similar to ours. And actually, this could repeat over and over again. Then you get a cyclic universe. This is something that Penrose, for example, has worked on. It could also be that if you go back in time, everything just slows down, and there's no singularity, but everything, moves less and less and less for an infinite amount of time. So no singularity. So this would be called asymptotic silence. There's an idea that time turns to space. So you turn from Lorentzian to Euclidean signature. This is called the no boundary proposal, and this is what Hawking and Hartle and so on have worked on. There could be neither space nor time. It could be something else entirely, like maybe a network that doesn't have any notion of geometry, and geometry only comes into being later. This is also something that physicists have talked about, written papers about. It could have been a black hole, it could have been a 5-dimensional black hole, it could have been string gas, it could have been a collision of higher dimensional membranes, and so on and so forth. Like there are dozens, if not hundreds, of those theories. And they all become possible because that early back in the universe, if you just go to times that are early and early enough, then you can change those equations whatever way you want, and there'll always be an initial state that fits to this. But a good scientific explanation must be simpler than the observation it's trying to explain. It also should be as simple as possible, and unnecessary assumptions are not allowed. The reason for this is just, if you have any theory and you allow to add unnecessary assumptions, then you could always add an assumption that says it was made by God or something. And this is clearly something you don't want to have in a scientific theory. And the issue with all those stories for the early universe, like the bounces and the string gases and so on and so forth, is that they are unnecessarily complicated. You don't need them. Like this simple model for cosmology that I started out with talking about, it's sometimes called the concordance model, or lambda CDM is maybe the better known words and so on. It does the trick. There's no need to make it more complicated. And I think scientists shouldn't make it more complicated than it has to be. So those theories for the beginning of the universe, they're mostly not wrong. I mean, there are some theories where we can, pick on the details, and maybe they're actually in disagreement with observations, but most of them are not wrong. But we can't tell that they're right either. It's not that they're in conflict with any data, but we can't look back in time to such early phases, and there is no rationale in our scientific method that would allow us to make a simple story more complicated. So I think they're modern creation myths. They're just written in the language of mathematics. And as I said, they're not wrong. You can believe in whichever one you like, but there's no evidence to actually back them up. And my friend Tim Palmer suggested to call this kind of idea ascientific. So they're not unscientific. It's not that they're wrong. It's fine to believe in them, but there's no evidence speaking for them either. So there's no evidence either for nor against them. So how did the universe begin? We don't know, and we may never know. The reason I say we may never know, I should have said this earlier, is that I think it's to do with the general structure of our theory. It comes from this split into an evolution or at an initial state. There is a possibility that we might be able to overcome this problem by developing an entirely new type of theory that doesn't rely on an evolution or on an initial state, but at least at the moment we don't have such a theory, and I have no idea what it might look like. Okay, so the next question is, do copies of us exist? So this sounds a little bit crazy, but there are actually quite a few physicists who believe that this is actually the case. And there are various reasons for this. They all go under the name multiverse, which is this idea that our universe isn't the only one, but there are actually infinitely many others. And there are multiple multiverses, and I'm not going to talk about all of them, but I want to briefly remind you of the most common ones, so to speak. First of all, there's eternal inflation, which is very closely related to Einstein's theory of general relativity and the story with the Big Bang that we just talked about. But what you do is that at an early time, you add a phase of exponentially fast expansion. This is called inflation. And then in eternal inflation in particular, this exponential expansion doesn't just happen in our universe, but it happens in a much, much larger, infinitely large space in which there isn't only one Big Bang, but there are lots of small bubbles that form in this infinitely large universe that can grow by way of the normal inflation into universes that look like our own. So there are infinitely many Big Bangs, and they continue to happen as we speak. So there are infinitely many universes. And there are different variations of eternal inflation, and you can have them, for example, with changes in the constants of nature. So you would have slightly different laws of nature, changes like the mass of the Higgs boson or something is a typical parameter that might be different in another universe. The problem with this idea is that there are no observations that can refute or confirm that these copies exist, because they're completely causally disconnected from us. There's no interaction that we can have with those universes, not even in principle. They just appear in the mathematics. There's actually a simpler version of this, which is that in an infinitely large universe, you have infinite variations of those fluctuations in the plasma in the early universe that leads to the formation of structures that later form stars and galaxies and planets and ultimately us. So in short, infinity is really, really weird. If you just have enough space, if you just have enough time, then everything that can happen will happen, and it will happen infinitely often. So in this infinitely large universe, there should be copies of our planet, of you and me, and everyone on those planets, with teeny tiny variations. Maybe there's a single molecule in your DNA that's a tiny little bit different. Or maybe, at some point in your life, you made one decision that was a little bit different that changes the history of mankind, or God knows. So everything that is possible will actually happen in an infinitely large universe than that. But again, the issue is we can't communicate with anything outside our cosmological horizon because the speed of light is finite. This is what the cosmological horizon is. It's the area with which we can communicate, and it's finite because the speed of light is finite. So we can't reach those copies of us if they exist, and there are no observations that can refute or confirm that they are actually real. And to add a third example of multiverse, that's what happens in the many worlds interpretation of quantum mechanics. So I previously talked about the measurement collapse. So in the moment you make a measurement, the wave function updates to what you actually measured. Strictly speaking, this is only one particular interpretation of quantum mechanics. It's often called the Copenhagen interpretation, or just the standard interpretation. It's the interpretation that is, at least at the moment, typically taught to students. But the many worlds interpretation is an alternative interpretation. And it says that it's not, when you make a measurement, it's not that all the other possibilities disappear, but instead the universe splits. So each time you make a measurement, you create a universe for each possible outcome. So just to give you a simple example, suppose you have a single photon and you send it through a beam splitter. So it has a 50% chance of going left, 50% chance of going right. Then you create two universes, one in which the photon went left and you observe it on the left, and one in which it went right and you observe it on the right. And now you have to multiply this with all possible measurement that could happen. And indeed, so those the word measurement in quantum mechanics it's a little bit misleading, because it doesn't actually require measurement apparatus, and it certainly doesn't require any consciousness or something. It just requires a sufficiently big thing. It could be you, could be your eye, or it could be some kind of screen, but it could also be I don't know, a banana or something. Those splits of the universe happen all the time and everywhere around us, and so there are really many of those worlds, which is why it's called many world. Now, you can probably guess what I'm about to say. The problem is there are no observations that can refute or confirm that these copies exist, because we only observe one outcome of the measurement. That's the one that happens in our universe if you're a many worlds person, but there's no way you can make any contact to those other possible outcomes. So what are we to make of this? So why do physicists believe in those things to begin with? Well, it's quite interesting if you look at the reasons they put forward for believing in this. It's basically, it's in all of those cases, it's the same argument, even though they're different theories. It's because they have a theory that makes some predictions that agree with what we observe. Then they conclude that all the math that appears in this theory also has to be real. But just because there's math for it, just because you can write it down, doesn't mean it's real. And you can assume it's real. If you have your eternal inflation and there are other big bangs in your mathematics, you can assume that the universes that seem to correspond to those equations exist, but that would be an unnecessary hypothesis. And so scientifically, it's not allowed. So science can't tell you that those copies exist. It also can't tell you that they do not exist. So this is another example of an ascientific idea. You can believe in them if you want to, but science doesn't tell you whether they do or don't exist. Okay, so this brings me to my last question, which is a little bit different. So it's the question, can particles think? This sounds a little bit crazy at first, and I think when I'm done, it'll still sound crazy. But so this is an idea that's called panpsychism, which basically it means that everything is a little bit conscious because it contains some stuff that's called proto-consciousness. And if you lump together sufficiently many things with the proto-consciousness, you get a proper consciousness like we have in our brain. So at least this is the idea. There are two different ways that people talk about panpsychism. And the one version, this proto-consciousness isn't physically real. So this is just a weird version of dualism where you have the physical world and then you have a completely detached mental world that can't affect the physical world and not the other way around. And this is fine. There's nothing wrong with it. I'm not entirely sure why you would want to believe in it, but it's not wrong. So this is another ascientific idea. But the hardcore panpsychists, they want the consciousness stuff to be physically real because they wanted to actually explain something physical, which is our brain and what it can do. Now, this is the point where I, as a physicist, get a problem, because if the stuff is physically real, then it better agree with what we know about physics. And so here's the problem. If you believe this kind of stuff, you have to believe that elementary particles are conscious. And so this is a summary of the elementary particles that we know. They're collected in the standard model of particle physics. You have probably heard of some of them, like the electron. I think this is the best known one. And the photon and the Higgs. Everyone knows the Higgs now. You don't have to count them. They're 25. I've counted them for you. We know the properties of those particles. They can be uniquely identified by something that we call quantum numbers. The quantum numbers of particles are things like the electric charge or the spin, and then there are some lesser known things like the weak hypercharge and stuff like this. It doesn't really matter. The point is you can write them down. It's just a list of numbers. And so the thing is that those numbers, they uniquely identify the particle, and they're all the same, those particles. And now the thing is, if you wanted a particle to have something like consciousness or proto-consciousness, then it has to have some features. It has to be possible to vary the thing. If it doesn't have any properties, then you can't do anything with it. But the issue is you can't add any properties to the elementary particles. That would be just incompatible with observations. The issue is, in a nutshell, that in quantum mechanics, everything that can happen does happen. So if we make a particle collision, and here's an example of a particle collision as it takes place at the LHC. So the axis of the beam actually goes perpendicular to the slide, and the two beams run into each other, and then there are lots of particles being created, and they go out and they run into the detector. And from all this data, you can reconstruct what happened in the interaction. And by help of the standard model of particle physics, you can calculate very precisely how many particles of which type should be created in those collisions. And the observations agree very, very well with the predictions from the standard model, which is something that a lot of particle physicists are not particularly happy with, by the way, because they were hoping they would find some new physics, but the standard model does just fine. Now, the issue is if those elementary particles had any internal states, anything, doesn't really matter what it is, then those could be produced in the different variety in those particle collisions, and that would change the number of the particles that are created. So it just doesn't agree with observations. The consequence of this is that proto-consciousness can only exist if it has no physical properties whatsoever, in which case it does not explain any observation. So do particles think? No, they don't think. Yeah, so I want to come back to the reason for the original title of the book. As I said in the beginning, I wanted to call it More Than This. And the reason is that I think a lot of people have somewhat of a bad start with physics in school. You know, they come to think that physics is just about atoms or things rolling down inclined planes or you know, a prism. And those are two images that you find if you do an image search for physics icons. And this is a pretty good summary, I think, of what people think physics is about. And I hope what I got across in this talk is that physics is about so much more than this. It's about the fundamental laws of nature that define our own existence. And this is why I wrote my book. And I have a lot more questions in the book with the answers. And yeah, that's it. Thank you for your attention.
Clapping for everybody. So, okay, there have been some questions posed in chat, but I find them rather obscure. So I'm going to ask some questions of my own, if you don't mind. And you probably can guess what they're going to be. So I've got to start by talking about, by asking you about free will.
Yes, I saw this coming. No
yeah,
surprise.
So
you're very predictable.
I know, very predictable. So which means I guess I don't have free will. So explain your position on free will. And I suppose you're going to have to get into this idea called superdeterminism at some point, or maybe that's a separate question. I'll leave that up to you.
Yeah, I don't think that they're connected, but I'm happy to talk about both of them. So the issue with free will is that no two people mean the same thing when they talk about free will. So the way that I've approached the topic in my book was to talk about what the fundamental laws of nature tell us about free will without actually talking about free will. So in particular, I've been talking about whether the laws are deterministic or not. How much do we know about this? And I said this in my talk. So we have those evolution laws. They're time reversible. They're also deterministic. So basically, it means that the present state of the universe and also the state of you and I, it was just caused by an even earlier state, and that came from an even earlier state all the way back to the Big Bang or whatever else you want to put there. So that's the deterministic part. And then in quantum mechanics, if you actually believe that quantum mechanics is correct, which I don't believe, but if you believe it, then you have an additional random element that happens every once in a while. You have one of those random jumps, but those random jumps are not influenced by us because they are not influenced by anything. That's what it means for them to be entirely random. And now the question is, like, if you know this, if you know the fundamental laws of everything, that everything is made up of, are a combination of being deterministic with this occasional random jump, do you think you have free will? And my answer to this would just be no. It doesn't really make any sense to me. So this is why I say free will doesn't exist. Let's just move on. It's not particularly interesting question, but of course other people have put forward definitions of free will that are perfectly compatible with the fundamental laws of nature, which you certainly know about, and I don't have a problem with that. In the end, it's just a definition.
Okay, I mean, unless it's going to be too technical, can you explain what superdeterminism is and why you think it's plausible?
Well, so I'm totally with Einstein that the non-local collapse of the wave function is a big problem. And I think that this is the main reason why we haven't been able to combine quantum mechanics with general relativity, because it has this built-in non-locality. This is exactly why Einstein worried about. And now you've almost certainly heard of Bell's theorem. So Bell's theorem is often summarized by saying that you can't have local hidden variables theories.
Somebody's got their audio on, thanks.
Okay, so hidden variables theories were believed to be a possibility to reintroduce.
Oh, I'm sorry, I just muted you, Sabine. Can you turn your...
Okay,
Yeah.
so where did you shut me up? Basically, where?
Not
Okay, so where was I? Oh yeah, Bell's theorem. Right. So what you can try to do is you can say, well, maybe the properties of quantum states were actually determined much sooner before you made the measurement, and they actually went to the measurement outcome locally. And this is what's called a hidden variables theory. So in a hidden variables theory, you don't have those weird things with particles in two states at the same time and all that kind of stuff. It's actually only in one state. You just don't know which. So this is kind of very much based on this classical thinking. And Bell's theorem says, to make a long story short, no, you can't do it unless you violate an assumption that's called statistical independence. And that's what's called superdeterminism. And I'm super unhappy with the name because it kind of suggests that it's more deterministic than deterministic, which doesn't really make any sense. Superdeterministic theories are exactly as deterministic as normally deterministic theories. They just violate this assumption that's called statistical independence. And there's a lot of controversy around what it actually means and if you actually need it for anything. But that's a short summary.
So I want to ask you sort of a big question, and I know we're already a little past 3 o'clock, but you know, you raise a lot of interesting questions in your book, and so just to I want to give you a couple of these. So one comes from my coverage of physics in the 90s and 80s. That's when I started my career. There was this idea that physics was going to explain everything. You know, you had this crazy phrase, theory of everything, for a unified theory of physics. The idea was that it would tell us how the universe came to be, why the universe has this particular structure, which allows for our existence rather than something else. Maybe it would even explain consciousness somehow. So physics had this immense potential. And I just wonder if, as time goes on, it looks like we were going through, or physics was going through, some kind of temporary insanity that explained this enormous arrogance and confidence that it could really explain the world. Or do you still have that belief? Do you still think physics is capable of that?
Well, I never had this belief. I guess I'm kind of, I'm a little bit, I'm not quite old enough. So I think it was the generation before me. And I think historically it's understandable because so after general relativity and quantum mechanics at the beginning of the past century, they made a lot of progress really quickly in the foundations of physics, like with the weak nuclear force, strong nuclear force. They put the standard model together. It all happened like within 50 years or something, and they had confirmed the whole thing, and it was just mad, you know. I think at this point, so in the 70s, mid-late 70s, they thought they were really, really close to finding this fundamental theory that would just be the last word about the foundations of physics. And the only thing that seemed to be missing was that the Standard Model didn't want to cooperate with Einstein's theory of general relativity. Now, of course, today we know how it went. They still don't cooperate, and we still don't know how it works. But then at this time, someone had just proposed string theory. Actually, not someone, several people. But let's not make this a history lesson. And it looked really promising. And then there was supersymmetry, and everyone was really excited. And then the trouble began, because they started making some predictions from grand unified models and from supersymmetry and so on, and those didn't work out. They didn't find those particles. And now every time it happened that they made a prediction, they didn't find the thing, they went back to the drawing board and they fumbled around with the theory, thinking, oh, it's got to be something like that, right? It has to work somehow. We're so close to this theory of everything. And it continued to not work. And I think somewhere around, it's kind of hard to say exactly when it happened, but certainly when I made my PhD, which was in 2003, people had kind of become quite skeptical already of this. It's called a top-down approach. You just go and you guess some mathematics, and then you try to find the lower theories, like the Standard Model, general relativity, in them. And they were all putting their hopes on the Large Hadron Collider, and then it was delayed and it was delayed, but eventually it turned on, and then it had to be turned off immediately because of I don't know, it was something with the vacuum or the beam pipe or the cooling or what, something. In any case, they found the Higgs and nothing else. And I think at this point in time, this idea of a theory of everything is pretty much dead. People would settle for pretty much any news in the foundations of physics at this point. It's like there's nothing happening, like nothing's happened, nothing of fundamental significance. I mean, they have found a lot of quasi particles and bound states and all that kind of stuff. Since the development of the Standard Model was completed. Oh yeah, they've reintroduced the cosmological constant, but this was already Einstein's idea. So I don't think that this idea of a theory of everything, it's not particularly popular anymore at the moment. Certainly not among the younger people. I mean, there's still people who believe in it and who work on it, but I think a lot of them have a much more pragmatic perspective now. And I search for dark matter, quantum computing, lots of quantum stuff now going on.
So you mentioned, okay, I'll make this my last question. I know it's late there in Germany. You just mentioned quantum computing. It seems to me that quantum computing is exciting for two reasons. One, it's a potentially powerful technology that can maybe lead us in new directions. I'm not sure anybody really knows where it's going to go. And it might fall on its face, of course. But it seems also that it's an application of quantum mechanics that might illuminate quantum mechanics and might help solve some of the paradoxes of quantum mechanics. So I just wonder what your take is on quantum computing and whether it can kind of give physics in general the jump start that it seems to need right now.
Yeah, that's a very good point. I'm personally hugely skeptical that we'll see a commercially interesting quantum computer in the next 20 years or even within my lifetime. It's like I think the technological problems are just immense. Of course, there are people who disagree with me, but I guess, let's wait 20 years and see how it works. And I can talk about this for a longer time, but I think that's enough. But it is still true that quantum computers are super interesting from the perspective of the foundations of physics, because they probe a parameter space that we have never been able to measure before. And it's quite conceivably possible that they just stumble over something that they can't explain, and it'll just open the door to some breakthroughs in the foundations of physics. So even though I'm not sold on all those supposed applications for industry and quantum chemistry and financial things and whatever that they're talking about, I'm not buying this. I still think it's a very interesting research direction, and we should definitely continue it.
Okay, I was hoping we could end on a positive note, and you just gave it to us. So thank you so much, Sabine. I really appreciate you coming, and I hope to see you online again soon.
Okay, cool.
And thank you everybody for coming. See you later.